Now, an important takeaway from the previous example is that if you're trying to find the area bounded between the graph of two different functions and the interval over which you're considering them, so in this last case it was 0 to pi over 2, if those two functions happen to have an intersection point over that interval, or in that interval, which they did here, you're going to have to use the x-coordinate of that point, which here was pi over 4, and you're going to have to split it up into the sum of two separate areas. So that's something that generalizes to any number of regions. So for example, this note says, and I'm going to draw a picture in a moment, we must split up the integral at each point of intersection in order to get the correct result, because there may be more than one point of intersection. Like in the last example, we only had one point of intersection, but there could be 2 or 3 or 10, right? There's no limit, really. So let me draw you a picture of what can, that kind of nicely illustrates what can happen without getting too carried away. So I'm going to draw a picture of two graphs that actually intersect at 2 points within a certain interval of consideration. So here's what we're going to look at. So here's one function, and I'm going to call this the graph of some function g. So we'll call this y equals g of x. That's the equation that represents that graph. And then the other function is going to come up like this, down like this, and then something like that. Right, and now I'm going to actually emphasize the points of intersection here. And then let's say we wanted to calculate the area that was bounded between these two curves. And I guess I should give the other one a name. Let's call the other one f. It'll turn out to be convenient to have f be the one that labels the lower one. Now, let's say you're trying to find the area bounded between these two curves. Well, you're talking now about this area here, which really, that you could give that a label, call that A1. This area here, which I'll call A2. And then finally this area here, which I'll call A3. Really what you're doing, if you're talking about the area bounded between those two curves, you're talking about the sum of those three areas. So you'd measure them each separately and then add them up together. So how would you calculate them? Well, you're going to need the x-coordinates of each of these 4 points. So let's give them names. I'm just going to give them a label. So we can call that one A, the x-coordinate of this point. A, we'll call the x-coordinate of this point. B, this one can say, or we'll call it C, and then how about this one, we'll call the x-coordinate D. So if you were trying to calculate this area, you would do the following. You would just do them one at a time. So you would, first of all, if I want to calculate A1, you'd say A1 is the definite integral. What are the endpoints? They're going to be the x-coordinates of these two intersection points. So you've got A and B as your endpoints. And now for the upper and lower function, well, you just have to be paying attention and be careful. So what's the upper function? That's this one here. So if you follow it along, sure enough, it's f of x. So the upper function would be f of x. And then the bottom, the lower function, the lower boundary, if you trace that one, you're going to get to actually g of x. So the lower function is g of x. And then, of course, you're going to integrate that with respect to x. So that's going to give you the definite integral that measures the area of this region here, A1. For A2, you'll just handle it for its own merits, right? A2 is the definite integral. Well, now your endpoints are b and c, right? These two x values. So you'd have the definite integral from b to c. And your upper function, well, what's the upper function? It's g, actually, this time. G is the upper function. That's the one that's going up at the top. So you're going to have g of x as your upper function. And then your lower function, well, it's probably got to be the other one, right? But nonetheless, this is what you would do. You would check carefully. So this is going to be f of x. So f of x is going to be the lower function. So they traded places, right? They traded roles. For the second region, g is actually the upper function and f is the lower function. And their bounds were b to c. And then for A3, well, again, just look at it for its own merits, right? It's the definite integral. This region, the endpoints are c and d, so it's the definite integral from c to d. Your upper function, well, that's f again, like the first one was, and then the lower function is g. So you're going to have f of x minus g of x. Okay, so that's really the process that you would use to find an area like this. Now, what happens if it intersects more than 2 times within your main interval. So you could say the main interval is between A and D, the two outermost intersection points. Well, what if there was a whole bunch of points in here where it intersected, more than just the 2 points B and C? Well, then you'd have to divide your area up even further, and you might have 10 of these separate areas to calculate, or 5 of them, or 20, right? It depends on the situation, how complicated it is. But in general, it can be any number of separate regions that you have to calculate. But that's the approach. You just break it down, calculate them one at a time. Now, what does this note here? In general, the exact area bounded between the graphs of a pair of functions f and g and 2 outermost endpoints a and b. So think about this just in general. A and b are the 2 outermost endpoints, and you want to find the area that's between f and g, between those 2 vertical lines as cutoffs. You can actually write down the area exactly correctly with one definite integral. There's a way to do it so that you only have to use a single definite integral. But it's not as good as it sounds. It doesn't really save you the work. You still have to do the same amount of work to calculate the area, but at least you can write it down symbolically with a single definite integral. And this is how you would do it. You can write down your area is the definite integral from your endpoint A to B, so area from A to B, and you can just go f of x minus g of x. And if I were to leave it like this, I'm not quite done, but if I were to leave it like this, what I'd really be saying is, well, I'm just going to trust the definite integral to work it all out, and I'm just going to have faith that it'll take care of the details for me. But here's what can go wrong if you just leave it like this. If you look at this picture here, notice how sometimes the upper function is f. But then over here, sometimes the upper function is g. What's going to end up happening if I just, as a blanket statement, go f of x minus g of x, I write my integrand like this for the entire interval, and I don't pay attention to when the curves intersect and when they trade places. What'll end up happening is regions like this, where g is the upper function and f is actually the lower function. It'll mean that this is exactly the negative of what I ought to be integrating, which means that this is going to come out as negative area. So what if I just did this approach? Here the outer endpoints were a and d, right? So take that into account. But if I had just taken the definite integral of f minus g from a all the way to d, and just not worried about these intersection points, what would have ended up happening is that this would have been counted as negative area. And that's not what you want. If you want the area bounded between the curves, you want all the area to be positive. So how do you take care of that? Without having to write this out 10 times, just put absolute value signs around the integrand, and that will take care of it. For any values where g is actually the upper function, the inside of the absolute value will be negative, and then the absolute value will just destroy that negative sign, and it'll fix it for you. So that's what ends up. And then for the places where f of x is indeed the top function, then the stuff inside here will be positive, and you can just throw the absolute value signs will have no effect, so they won't cause any harm. So that's how you can write down the area in general without having to pay too much attention to the intersection points. So then the question is, well, why don't we just do this all the time? Why would I bother showing you all this and breaking up into 3 separate integrals like we did, or in the previous example, we did 2 separate integrals. Why would I even do that if you can just do it in one line like this? Well, notice that all this does is give you a way to express the area. It doesn't give you a way to compute it without having to resort to the strategy that I laid out up here. You're still going to have to break your definite integral up into several definite integrals. It's going to be up to you to figure out where f of x minus g of x is positive, so that you can throw the absolute value signs away, or where g of x would be the upper function, and in that case, f of x minus g of x would be negative, and in that case, well, then you'd have to replace the absolute value signs with a negative sign, but that's something that has to be done manually. So it's not as good as it looks like it might be. It doesn't actually give you a way to bypass doing the work up here. And it boils down to the fact that we don't have a way to come up with an antiderivative for the absolute value sign, right? We don't have a method for coming up with an indefinite integral for the absolute value. So it's not something that's just going to save the day and make this an easy task. You're still going to have to find the points of intersection and break up the antiderivative. And I'm guilty of rambling a bit here, so I think let's move on, and I'll show you with the next example, which will hopefully clarify. So what do we got here? We want to find the area bounded between the graphs of these 2 functions, sine of x and cosine of 2x, and our outer endpoints are x equals 0 and x equals pi over 2, same as last example. So how are we going to do this? And another thing that's nice is by doing this method that I'm about to show you for this example, we won't even need to do the sketch. So that's actually something that some people will be happy about, because some people don't like drawing sketches of graphs, and that'll save you some grief here. You won't have to worry about sketching the graph. Okay, so how are we going to do this? Well, what we're going to need to do is find all the places between 0 and pi over 2 where these two graphs intersect. That's going to be the first step. That's what you want to do. Okay, so that's our first job. Find the points of intersection. Okay, and how that's going to be done is, first we're going to figure out where sine of x and cosine of 2x agree. So, well, and in fact that's the way we're going to find the points of intersection. That's not the first step, that is the step. That's what we're doing, right? So we want to solve the equation sine of x is equal to cosine of 2x. Okay, and the strategy that we're going to use to solve an equation like this is we're not just going to start plugging values in and try to cross our fingers and hope we get one that works. There is actually a neat strategy that we can use to solve this equation. What makes it tricky is not just that there's trig involved, but that the fact that one of the trig functions, cosine, actually has twice the angle of the other trig function. This one has x, this one has twice that much, twice x, right? So that's what makes this a little bit trickier. So what we're going to do is use one of the double angle identities. So let me remind you that cosine of 2x can be written as cos squared of x minus sine squared of x. That's what we're going to apply here to the right-hand side of this equation. So this is actually going to turn into sine of x is equal to cos squared of x minus sine squared of x. So that got a little bit better in the sense that now we still have sines and cosines, and unfortunately there's squares now involved. So that, in one sense, it kind of got a little bit more complicated, but at least they all have the same argument. They all have an x plugged into them. So that's actually a step in the right direction. And to take this a bit further, what would be even nicer is if it was all in terms of the same trig function, right? There's sines and cosines appearing. It would be nice if they were either all sines or all cosines. Now, it turns out that it's preferable to convert this into an equation that has only sine involved, because it just ends up working out nicer for that to do it that way. I'll show you what I mean. So what we're going to use is the Pythagorean identity. So another thing I'll remind you, if you have sine squared of x plus cos squared of x for any real number x, that's always equal to 1, right? So you can actually use this to relate sine and cosine and actually get rid of one or the other from this equation. Now, if you try to do this by getting rid of the getting rid of the sines, well, the sine squared here you can use the Pythagorean identity for. You can take this cos squared, subtract it to the other side, and you'd have sine squared of x is equal to 1 minus cos squared of x. And then you could replace this sine squared of x with 1 minus cos squared of x. And that would get all cosines on the right-hand side of the equation. However, you'd have difficulties removing the sine of x because this doesn't tell you how sine of x and cosine of x relate. It tells you how the square of sine of x and the square of cosine of x relates. And it's not impossible to change this into an equation that only involves cosines, but it's just so much easier to do it the other way around. So what we're going to do is just take this cos squared and get rid of it in terms of sine squared. So in other words, just take the sine squared of x, subtract it over to the other side of the equation, and you're going to have cos squared of x is equal to 1 minus sine squared of x, and that's what we'll plug in for here, for the cos squared here. So what you'll get is sine of x is equal to 1 minus sine squared of x minus sine squared of x. Okay, that's what you end up getting. So now that we've done that, we've converted everything into sine. So that's good. That's even better than what we had before. And we can even clean this up a bit by combining these two like terms, sine squared of x and sine squared of x. So we can write this as sine of x is equal to 1 minus 2 sine squared of x. And then finally, if we move everything over to the left-hand side of the equation, what we'll get is 2 sine squared of x plus sine of x minus 1 is equal to 0. And actually that is a quadratic in sine of x. And what I mean by that, quadratic in sine of x, that means if you were to make a substitution, say let u equal sine of x, then you can rewrite this equation as just 2u squared plus u minus 1 equals 0. And now, well, this can be solved. This is a quadratic. Just solve it like a quadratic. In fact, you can even factor this, right? Because you've got two numbers that add to positive 1, and they'd have to multiply to the product of 2 and negative 1. So you need two numbers that add to 1 and multiply to negative 2. And if you take positive 2 and negative 1, those will work. So you can write this as 2u squared plus 2u minus u minus 1 equals 0. And if I factor out a 2u from the first two terms, I'd have 2u times u plus 1. If you factor out a negative from the second two terms, you'd have negative u plus 1 equals 0. And now you've got two larger terms. You can pull out the common factor of u plus 1, and you'll end up with u plus 1 times 2u minus 1. Okay, great. So that's factored. Now we can get the solutions. This is going to be satisfied when u is equal to negative 1 or positive a half. These are the two solutions in the variable u to this quadratic here. But now we're interested in values of x which satisfy this equation, which is equivalent to saying which values of x can we plug in here to give us a value for this u that'll be one of these two solutions. That's really what it comes down to. So, well, in other words, when is sine of x equal to negative 1? Or when is sine of x equal to a half? So that's where we're at now. So we need, just going to summarize where we're at, we need sine of x is equal to negative 1, or sine of x is equal to a half. And remember, I mean, both of those two equations have infinitely many solutions, right? They will have, because sine of x oscillates back and forth between positive 1 and negative 1. So both of these equations, if you just look at them out of context, they have infinitely many solutions. But we're only interested in solutions that fall between 0 and pi over 2. Okay, so I'll leave it to you as an exercise to verify that this is correct. But the equation sine of x equals negative 1, this has no solutions in the intervals 0 to pi over 2. So this never happens in the interval 0 to pi over 2. But this equation does have a solution. If you look between 0 and 2 pi, there's two solutions, pi over 6 and 5 pi over 6. But the only one of those two solutions that falls between 0 and pi over 2 is pi over 6. So that's going to be the solution to this. So this happens when x is equal to pi over 6. So that is actually going to be how we break up our definite integral. And that's what we can do on the next page. We'll actually go ahead and finally calculate the area. But all of this work was just to find the intersection point between the graphs of these two functions. And sometimes that's the case, right? If we go back up to this picture here, sometimes the hardest part of finding this area is actually figuring out where the two curves intersect, and this is exactly one of those cases. This was the brunt of the work of the problem, actually, it turns out, and once we finish it in the next page. Okay, so I'll stop this here, and we can go ahead and do that on the next page.